Okay, second video on the normality of sample proportions for large sample sizes and various values of population proportion. We're going to move towards what's going to be called confidence intervals, which is important. So this is that little step just before confidence level or confidence intervals, which is a very common application of this stuff. So we're on our segue towards that. And we've learned that when we have distributions of the sample proportion for large sample sizes, okay, they're normally distributed very well approximated by normal distribution, where the mean of the sample proportion equals the population proportion, and the standard deviation of the population or the sample proportion is given by that expression there. And we may not know the real value. Okay, so this is an estimator, as we said in the previous video, for the population proportion. This means that the best estimate for the standard deviation is given by that, and that's all stuff we've done in the previous video. Now we also, if we stretch back a little bit further when we're looking at standardization, the z-score, we recall that the z-score is defined by the difference between the score minus the mean divided by the standard deviation. Okay, so by standardizing, we can say the distribution of the random variable z. What we do is basically sub it into that formula. So this implies the following for z. So I'm going to stuff the denominator and this expression back up here, and we're replacing sigma with our familiar expression, p hat times 1 minus p hat over n, and the square root is taken. And on the top, instead of score minus mu, we've got the sample proportion minus the population proportion. So we're just replacing them with corresponding aspects of the model that we've been using. Now, when we put this with what we've learned before about standard normal distributions, we can see the following emerge. We saw previously that 95% probability that a score lies within, we said, approximately 2 standard deviations of the mean. Okay, and we're combining that previous knowledge with what we just established. So written as a probability statement here, rounded to 2 decimal places. So z's within, that's really closer to 1.96 standard deviations above and below, yields a probability of 0.95. Writing that with the expression we just devised above there, the standard normality of that thing, and then multiplying through by this same thing that we just referred to. It means there'll be 1 on the denominator, and we'll have p hat take p. For an individual variable, it's upper p hat take p. And then you can see that the expression has been multiplied in all parts of the inequality. Okay, that's where it comes from. And it's not something, just going from this step to that step is not something that you're going to be likely to be asked to do, but that's where it comes from. Okay, we know that we're looking at an interval from here to here, alright, because you can see the corresponding z-score there, and then the standard deviation of the population, of the sample proportion here, here, thus here, here. That's the form of it, okay? And that's what's called a confidence interval, and we're going to talk about that properly in the next couple of videos. And this one here is actually what's called the 95% confidence interval, but there's other ones as well. So the tails combined each contain 5% of the distribution, 2.5 on each end, and the Z value is 1.96, and we've seen these Z scores before. Okay, so properly developed in the next video.